Okay, yeah, today's review will be, centered around these topics, moments, and relativity. And um, everybody should have, oops, where's my milk in here? The second part of your printouts, this one, semester two examination. Successfully, or you just completed it? Okay. Well, the answer for part A should be, um, let me see, 0.94. Yeah, it depends. Like I said, there's more than one way to do relativity, depending on which one you say is the stationary frame of reference. That's your choice, of course. Mm. Maybe he doesn't have a mic. Kwa, he might not be there. Hmm. Okay. Wow. Even though it says right here. Hmm. That's just tells you how people don't really focus or pay attention. Okay, we'll start in 2 minutes. It doesn't matter. If these people don't come, they come. Okay, so um, if everybody can hear me well, we're gonna get started. Just give me a thumbs up if you're ready and you can hear me clearly. Okay, so we're gonna start on this first problem, which deals with relativistic velocity. You guys know that there's steps to solving these type of problems. And one of these things is reading it carefully, and then we decide what our stationary and our moving frame of references are. So stationary and moving frame of references. Um, and this really depends on the velocity we're given and what that velocity is relative to which object. Okay, so as we read through this, there's three spaceships. We can see that this one's x is traveling to the right, so we know the velocity of x, and we can see the y and z are both traveling to the left with very similar, the same velocity, but to the left. And all of this is relative to the observer on Earth. Okay, so first we're gonna decide which way is positive or negative. So I just make a mark to indicate which direction I decided is positive. Sometimes the question will tell you, there are some questions I'll say going to the right is positive, and so that's when you have to make that direction positive. But in this situation, we decide for ourselves. Okay, so let's look at the question quickly. We already talked about this, the velocities, and we have a length as well. Okay, and that's it. Okay, we're asked to find the velocity of spaceship X relative to Y and Z. So these two are considered one. And so if we're asked to find the velocity of something relative to something, then this is usually the moving object, okay? Relative to this, and this is almost always the moving frame of reference. So for us, it's very easy then to establish which is the stationary one, which is the moving frame of reference, and then assign our velocities based on that. So we want to find the velocity of the moving object relative to the moving frame of reference, okay? So we have these two values and they're exactly the same, and this, because this is the stationary frame of reference, we have chosen this because these velocities are based on the observer on Earth. So now that means this velocity of the moving frame of reference is exactly what it says. Now because we said to the right is positive, we have to make this negative. Okay, that's important for our equation and how our answer will come out, and let us know what direction the relative velocity is. So based on this, I'm just going to quickly look at my equations. I already know which one I want to use. I want to find this one, so that's the one I'm going to end up using. Okay? Alright. Okay, so, I better just double check. Minus u and v. Okay, so what we have is our equation, and we're just going to write this right quick. And then we're just going to plug in our numbers. U is the, we want to find this one. So this is U because this is the moving object relative to the stationary frame of reference. So we know this one. Okay, so there's U. It's positive, and it's going to the right because it's positive. So we're going to put that in. 7 minus, and then we have v, which is this, it's negative, so we got minus negative 0.7 c. I better put that in, and that's going to be over negative 0.7 times negative 0.7, and our c is going to be crossed out. And then so we end up with this positive on top, okay? So 1.4 divided by whatever that is, negative 0.49. And, you know, your answer should come out. You'll see that this comes out to a positive answer, 0.940, okay? And that makes sense because we want to know how fast is this moving object relative to the moving frame of reference, and that it's going to the right. That makes sense that our answer is positive, okay? Because the way we chose our direction, which one's positive, which one's negative. Okay, so those are the steps. Read through this, identify where's your stationary frame of reference, what will be your moving frame of reference, and usually that moving frame of reference is the one that the object that we want to find the velocity of is relative to. Okay? Almost always like that. And then we identify, step 2, we identify which way is positive, and then determine our values of u, u prime, or v, depending on the question. Almost always you're going to find either this one or this one, but not always, sometimes that one, okay? Just usually. Okay, everybody good with that question? This type of question? Almost always some velocity type. Okay, state and explain which observer or spaceship will view spaceship Y as the longest and which will view the length as the shortest. So who will see Y as the longest? Who will see Y as the shortest? Okay, don't forget, also your answers should be 3 significant figures. Okay, so this one, we gotta say, well, let's see. Here's Y. If this is the velocity of X approaching Y, then that's going to be the same velocity of Y approaching X, but in the opposite direction. So that means this Y will have a length contraction relative to X, right? So we have a length contraction means the length of Y at 10 meters is not going to be seen as 10 meters for X because X experienced the greatest velocity and the greatest velocity closest to the speed of light. So Y shortest. Remember, we don't have to write full sentences for spaceship X, okay? You should say spaceship X, but I'm not writing it that much. And then, well, for Y and X, Y and Z here, you can see they're both traveling in the same direction. So basically, it's as if Y is not moving. Now, compared to someone on Earth, Y is moving. Okay, Y is moving, and it will also experience, although this picture shows the spaceship up here, it's probably more realistic if it's approaching towards the Earth, so that would be, again, length contraction, but at a slower velocity. So still length contraction to make it looking shorter due to the velocity of near the speed of light, okay? But compared to Z, it's as if Y is not moving. So y is longest for z or z. Okay? Now why is this? You have to say we gave the longest and shortest, but we have to give the reason. X sees y move at highest velocity, 0.940 c. So has greatest length contraction. Okay? And that should be your full answer. No, again, when you're writing explanation type answers, don't write full complicated sentences. It's very important you can answer this quickly with the main ideas. But please write more neat than I'm doing so I can read it. Okay. Okay. Everybody good with this? Any questions? Great. Great. No. No. No down ones. Good. Clear for everyone? Okay. Oh, all right. So we're gonna get to a moment's question. It looks like here, and this is what, a street pole or light pole. So what we're looking at is how the this vertical thing is supporting these horizontal ones, and at the end of them, these globes. Yeah? Okay. Let's see what we're asked to do. So we have a bunch of information here. That's good. I'm just going to circle it quickly so my eye will go here quickly. All right, I need to know these distances, so I can write them in real quick. 0.2, x, z to y, z to p, okay, 2.3, and then this one, it's a little shorter, it's going to be 0.35. I'm just going to write it there quick so that I know what's what. Okay, so this you can see is going to be balanced. This will have its own weight force. This one too, right there. And then in the middle, mass of support. Okay, support. So these ones also have their own. Okay. All right, so we know these ones 55, these ones at 25, which is, how many marks is this? Only 4 marks, so we got to get this quick. Calculate the tension in the metal strut. So that's this one here. All right, so I guess we're just going to concentrate on one side for now because they're both the same. And so if all of this is going this way and going this way, well, something has to go the other way. And so I believe at point P, we should put our pivot, okay? Why should I put it there? Because I don't know, this pole has a force acting on these. So we have a force here, and that is the tension this way. Why do I put the tension that way, and how do I know the tension is at this point? Well, there's a reason why they gave me these distances to this point, okay? Also, it's where the metal strut is touching this pole, which has the weight forces down. So I know that tension must be going this way, okay? It's always away from the load of this side. So now we have that. We also have P, point P, okay? And yeah, this side is exactly the same. We can just ignore it because, yeah. this side is going to act the same as this side, okay? Anyhow, let's start. So what is the tension in the strut? Well, we have our torque and our moments clockwise equals our sum of our moments anti-clockwise. Why am I doing this way? The reason is I don't know P, I don't know T, so there's two forces I don't know. And as you guys know, for any kind of equilibrium or moments, there are two situations. So we can do sum of the torque equal to 0, clockwise, anti-clockwise moments balance each other. And the second one is sum of the forces are also 0. So everything that's up is going to be equal by something that's down. Everything that's to the right is going to be equal to something to the left, so that they both equal to 0, all of them equal to 0, okay? And the sum of the forces is a little more than just the torque and the moments. All right, so we've decided, because we don't know two force points, we have to use the sum of the torque and moments. And then because we want to find tension, it's one of the unknowns, we will always put our pivot at the other one if there are more than one, okay? And almost always, if the distance is referenced to something that is a point where there's a force, you should know that's where a pivot could go, okay? Almost always that's where the pivot will go. Okay, so we have two anti-clockwise, and we have the tension. How do I know that these are anti-clockwise? So if I put my pen here, or a pencil, and I stick it across, that's perpendicular to the direction of the force. When I hold my pen here at the pivot and I push down, you will see the pen go this way. So that's when you know the direction of the force. Same with the tension. If the tension's that way, I put my pen perpendicular to it, and when I push the pen in the direction of the tension or the force, whatever it is, it will go this way, and then that's my clockwise, okay? So that's how I check to see which direction from the pivot the force is causing the member to turn. All right, so let's do this. Clockwise, we have the tension, and as we know, the equation for torque and moments is very simple. It's just going to be wherever I can find it. Here it is. If there's no angle, we can just ignore that. It's just radius times force. So we got the force of tension, we have the distance from the pivot, and of course that distance must be perpendicular. So if it's going to the right, the distance is from this downwards until we meet a parallel line. So you can see how the parallel lines of the torque direction and an imaginary horizontal line passing through the pivot. And then there is our distance, xy. We already know what it is because we wrote it out, 3.2 meters. Again, everything's in meters. And it's going to equal the anti-clockwise. So the first one we're going to have is the support, and it's this mass. It's going to be its weight force times the perpendicular distance. So the support is considered here. I guess in the middle of that. So the center of the support passes through the point where the metal strip connects to the thing. Okay. Acts through X. So where is X? There it is. It acts through X. I put it at the wrong spot. I should have read that a little bit better, but I double checked my work, okay? There we go. There's the distance of the support. So I'm just gonna remove this and put it back over to here, okay? And then, of course, our bulb and fitting, and its distance from the pivot is this entire length z to p, so it's 2.3. And then that's it. We've done everything, we've set it up, we have all our moments, and we have our counter moments. And now we'll just solve for t, because that's all it's asking us. Whatever that is, just write it here. I believe it all works out to 4.14 times 10 to the power of 3. And I'm just going to write it here. Okay, you can do all this, and you can show that step, whatever this is, this number A, this number B, and divided by that. You have to get a mark for showing this work. I know you guys like to use solver for your calculator, so I ended up just probably just marking this one, this one, this one, and the answer. Okay. Any questions here? Everybody good? Yes, this one's easy and basic. We'll get to a different, we'll just warm it up. Here you go. Okay, 3 marks. The minimum that the drink can be placed with the tray will be make it unstable. It means that something is gonna tip over, right? So we just read this quick. Mass of drink, okay. Uniform length of this, and then we have our tray mass. Okay, so our tray mass, and this is determine the minimum distance from X that the drink can be placed to make the tray unstable. Okay. So where is our pivot going to be? Where are the forces? So we're going to draw where our forces are. We have the drink. We have the tray. And we have to determine the tray is this, so we know this distance, by the way, for the tray. It's half of that. You can just do it quickly in your head. It's best. Calculator's fine too. Okay. We have that. This is X. That's what we want to find. And we got to set up our equation from this. So which is our pivot's going to be here. Okay. Okay, good. So now we know this distance. Maybe. We don't know quite yet. Do we? Or do we? The minimum distance is replaced. Okay. So we come up with our equation. Again, it's going to be sum of the torque at moments, because we have 2 unknowns, I think. Do we have one? Well, we have 1. We don't know this force, and we don't know the total force. Okay, clockwise, sum of the torque and moments. Anti-clockwise, okay, so we have the drink weight, which is 0.29 times 9.8. That's anti-clockwise. I should put it the other way. And that's going to be our distance x. Okay? There. And then, what do we have? We have our drink. Now, we don't know this distance yet. All we know is the total distance of the center of where the center of mass for the tray is, and supposedly where this is right now. So yeah, so we can work that out. We can find that distance here for the tray's center of mass to there. It's going to be these two minus each other. So the tray is 0.3 37 times 9.8, and it's going to multiply this distance, and this distance is this one minus this one. So we got 37 minus 27. Now that's an easy number to do in your head, and then we should be able to find the rest of this. Okay? We don't know what this is, but we know where that is. Yep. Whatever that is equals A divided by that. And it says here the answer should be in centimeters. So, you know, these distances have been inputted as meters. Just remember to convert it to centimeters. I should have put that in centimeters. I did, didn't I? No, I put it in. Okay, so there we go. I believe you should get something of 12.8. Make sure you have three numbers, three significant figures, as we do in every question. 1, 2, 3. That's important. Okay? Any questions about this? Okay. Everybody good? All right. Okay, now this is a good one for understanding the principles. The diagram shows a fence that is in equilibrium. We know there's equilibrium here. Each of the fence wires has tension, and the support wire is tension S. So these ones are the support wire, the fence wires, and this is the support wire. State the direction of the reaction force exerted by the ground on the fence post. So here's the ground, and we want to know what direction the ground is doing. So right now, well, again, if anytime we have we know that this is horizontal, we know there's a weight force that's vertical, and that's what we like. We like to see only horizontal and only vertical forces. Whenever we get one at an angle, we need to break it down to its components. So this one is to downwards and to the right. So we have a horizontal right from this. You can notice that my length is exactly the length of this, and a downwards force. So that makes sense. If this is an equilibrium, this in the x direction will equal these three. And this downwards one, is xy. Oh, and we have downwards mg. Well, state the direction of the reaction force of the ground. Well, the reaction force of the ground will be, we have down, down. We need a balance. We have a balance of here, of the horizontal. So that means that this must be up. Okay, so that we can have a balance of forces, because it says it's in equilibrium. Okay, there we go. It is noticed that when the tension and the fence are increased, so the force exerted by the ground on the fence post also increases. With reference to conditions required for equilibrium, account for this observation. So why? Why is the ground creating more upward force? Well, let's take a look again at what the support wire is doing. The support wire is both going to the left and downwards. So if the T's increase, then the support wire, its horizontal component must increase to match this, to equal this. However, the support wire is not just only the horizontal. The only way we can increase the horizontal is by increasing the tension in the support wire, the total tension. So this is the real force. These are just the components that create this, and this must increase so that this can increase. And so if the resultant direction of the tension in the support wire must increase, then that will increase its vertical downwards force. Okay? So let's write as tension increases, horizontal. Remember, I can write this, but I can't just write that because the person who's going to be marking this might not quite understand what that means, unless you draw on your diagram like this. But you have to say, you should really say horizontal component of S must increase. For equilibrium. Okay, there we go. And now, so that means S tension overall must increase. Must increase. You should be writing the words. Must increase. Which causes the S downwards to increase. Reaction force upwards must increase to maintain equilibrium. Okay. So that's it. You have to look at the overall forces. What is balancing this tension to the left? The tension of the support wire to the right. Now, to increase that, you have to increase the overall tension in the wire itself, which is at an angle. And if that increases, any other horizontal or vertical component will increase as well. And then as that increases, that vertical downwards increases, the reaction force upwards must increase to maintain that equilibrium. Okay? It's good. It's good news. Good news, everybody. All right, we're going to do one more. Oh, there's part B. There is a part B to this. Two part Bs. Two part Bs? Did I mess up again somehow? Yes, I did. The flagpole. I did mess up. Okay, this is from semester 2 or what? Or 1? Let me double check. Oh, semester 1. What question would this be? Flagpole. Got it here, so no problem. There it is. Okay. Sorry, guys. Usually when I do that, I'm doing it by page numbers, so I don't see all of it, but I guess I should have included page 25. This one, yes. So show the tension in the rope. Okay. So if you want to quickly sketch this somewhere on that page of yours, maybe as this page, there's some room here. Okay. Yeah. 14 questions. Good. 14 marks, I mean. All right. So show the tension in the rope. First, we had to determine where it's touching something, right? And you might think, oh, it's touching the ground here, it's touching the pole. Really, the main object is the flagpole. So we consider the tension to be connected to the flagpole there, and that it's there. Okay? The flagpole itself has a mass, and it's going to be in the center of that, and that mass is going to be downwards. And then we have a reaction force at P, because again, that's part of the pole touching the ground now. And we're going to assume, well, tension we notice is downwards and to the left. Wave force is always downwards, so we need something that goes up. And to counter this left tension, we need something that goes a bit to the right. So we can assume that this is going up something like that. Okay? And that's how I assume that, depending on the other ones. That's all we have. We only have tension from a rope. We have the weight force of the flagpole, and we have where the flagpole touches the ground. So then, that's a very good assumption of which direction that is, okay? Now we're asked to find the tension in the rope. That is exact, approximately 70 newtons. So that means this one we have to find. We don't know R. So right away, by me establishing that, I know where to put my pivot. I want to find T. I don't know R. I put my pivot at that unknown point. Okay? Yeah, so that's it. Same, but slightly different. Show the tension is approximately 70. Now, why is this so complicated? Well, because of the different angles. So we have the angle here. We have, I'm just going to draw out the two components. Because the tension is at an angle, I need to know my two components of this. Okay, so there we go. And these two components will act independently. Okay, so this one to the left, well, if this is my pivot, it will cause an anti-clockwise. So now I'm establishing the direction these are going. And because these two are downwards and to the right of the pivot, they're going to cause a clockwise. So we have three forces. Not really, we have just the tension, but it has its components. And its components are different. Okay, this is what would make this type of question tricky, that part. All right, so let's establish our equation now. Now that we know, oh, no, I'm sorry, we are missing some information. We need our R value. So this one will be, well, where is it attached? Let's take a look at our things now. Are using a rope slowly raised? Okay, so the pole is that long. So one thing we know is that this radius for that must be perpendicular to its direction. So that's R. And this one will be the length, which we consider to be half the length of the pole itself. So that's 2.1. We know this distance is 2.1 meters. And we really want to know this part of the triangle it creates. Okay? So we know this is 2.1. We know that's 62. And we want to find this distance here. So what we have is a right angle triangle. We have hypotenuse and we have this. So we want to find the adjacent side, and we know the hypotenuse. So what do we use? We use cosine. So we know this, and we want to find cosine of 62. Why is it cosine? It's the adjacent side and the hypotenuse of the angle. Okay? All right, so we have the distance for that. What about this one? This one's going to be the same pivot point, but now it's going to be slightly further. Where is the cable tied along the pole? It's going to tell us somewhere up here. 2/3 of the way up the flagpole. The rope is attached 2/3 of the way up. So 2/3 of that, 2/3 of 4.2. Do it on your calculator. Was that 16? 16? No. Okay, I'm just gonna do 8, 6, 3. I don't know. Need a calculator. That's 2.8. So ours is gonna be 2.8 now. This is 2.8. And so that R is 2.8. Same. Cosine 60, whatever. Okay? And then lastly, how high is this one? Is the height of that. So we already know its distance. So this time we want to find that one. We're going to call it Y. And that one is going to be R equals 2.8. And because it's the side that's equal to this, so it's opposite, it should be sine of that angle, 62. Okay, so sine is always the one that's opposite the angle if this horizontal is below everything. Okay, so we have our distances. This is why this is worth 5 marks, okay? All right, so now we're gonna, of course, because we have 2 unknown forces, we're gonna use our sum of the torque, sum of the moments. Okay, clockwise, we have these two. We have mg, which is 9.1 for the flagpole. Okay, 9.1. There's our force. Our distance of that is this one here. I don't recommend doing the calculations separate and then putting it in here because it's going to take time to do that and you're going to have to write it again and again. So better just to put it into one equation. So we have the clockwise moments, force, the distance of the flagpole itself, and now the Ty is going to be what we want to find, right? Okay, so Ty. Now, what is Ty? Anybody? Hello? Ty, what's its distance? Now Ty is based on Tx, yes? Or sorry, T. So Ty is going to be T, and because it's opposite the angle, sine 62. Yeah? Oh, not 62. My bad, my bad. Over here, over here, over here. Let me just erase that. So T's component are based on the 30 degrees, not the 62. So it's going to be sine 30. And then tx, we need that value too based. Why can I not use these? Because I need to solve for t, and if I have these two different ones, it's going to mess up my thing. So then t x is going to be cosine 30. Okay? And now we just have one variable that we need to find. So t equals sine 30. There's our force. It's going to multiply by its distance, which is that. We already established that. 2.8 cosine 62. And that's going to equal the other side, the anti-clockwise, was tx, and then we said tx is this, so it's going to be tx cosine 30 and multiplied by its distance. Again, it looks confusing at first, especially if you have to write this all out in one go, but you do it step by step. What is the force? What is the perpendicular distance? And it's always the same, okay? Force times perpendicular plus anything else that's in the same, that's causing the same direction of moments. So the ty is a component of the tension. So t sine 30, there's our force. That's the one we want to find. And then it's perpendicular distance. Now the x is just the horizontal part. So tx, and then we know that vertical distance, it's perpendicular distance. So now we have our radius. Yeah. And this, you'll notice the angles are different because it depends on this one, it depends on where it's located on the pole, which is based on that angle. And then the tension component is based on the angle of the rope, okay? So that's why it has to be different. Is everybody good with that? Good so far? Okay, so now, do some moving around of the numbers and solve for t, okay? Let me know anybody has found the answer for it. I'll write it here for you, but I want you to try to calculate it first. Oh man, did I forget one? There's a flag there too, folks. Don't forget to add that one. There is a flag here. I can get, let me see. Which way is it going? It's clockwise. We're just gonna add it to this side. Um, Terrible, my bad. So the flag is 0.7, so it's gonna be on this side anyways. We don't have to add it to that side. 5, yep, times 9.8, and the distance will be this 4.2 times sine, no, cosine 62. So four point two times cosine 62. Okay, there we go. So we need to add that into your equation on the left hand side, if you will. And your answer should come out to something approximately 70. Did anybody get that? Great. I think my calculator came out to about 69.1, which is approximately 70 newtons. Okay? Now I tried it the first time. It gave me like 59 because I forgot the flag. I didn't read the whole question. Ooh, easy to miss these things. Okay, but that's why we identify all the forces that are there. And if we miss one, especially this, when it says something like this, it's very easy to catch yourself and say, okay, what did I miss? But yeah, I missed that one. My bad. But there's the flag, the pole, and the rope. Okay. That's how we do it. We're going to move to part B here, and you should have the paper you have. Determine the magnitude of the reaction force and the direction relative to horizontal acting at the pivot point. So that means what is it, and relative to the horizontal means what's its angle this way, okay? We already established that it has to go that way. So it's the only one that has a horizontal component, so it has to go to the right to counter the tension, and it's the only one going up, so it has to go up as well. So we kind of already know what direction we are looking for, okay? And for this, we don't have to use any more tension. Remember, there's a second component because we already know all the other, I don't know, directions, components. Then it's easy for us to find all the vertical ones, the forces, some of the forces up, and some of the forces, you know, horizontal, up and down, okay? So we know it's gonna go to the right. I don't even know why I put those extra arrows in. And we know it's gonna go up. So that means everything's gonna go down. R equals T down. T down is Ty, so Ty is here for us, okay? All right. T sine 30. We know the flagpole is 9.1, and we know the flag itself is 0.75. And you know, those two can be added together. You can skip a step there if you wish. 9.1 plus 0.75. Because they're both weight forces, what I can do is just multiply, add the weights together, their masses, and then multiply by 9.8 together. And there is all our vertical ones. And then for the horizontal, well, this is only Tx. And Tx we know is cosine of 30 of T, okay? And we know T, if you guys are asked to, find this, just use the values that's given to you here, okay? Because maybe you got this wrong. Like in a question where they say don't approve it, but just find the tension. Maybe you got it wrong, so you just put it in here. So we got 70, sine 30, all that, plus this. And for that one, you should get 131.1. And this one, is whatever cosine of 70 is going to be roughly 60.1. Okay? So once we have these two components of R, well, these two components, they make the resolution, the resultant. So R equals the square root of those two squared. The sum of the square of the two sides, because they create that right angle triangle. So now we have the magnitude and we have the direction. The direction is almost always going to be tangent, okay? Because these two are the sides, so we're always going to use tangent of the opposite side. So we want this angle horizontal. But if we look at the triangle, let me just draw it a little neater here. If we look at the triangle, we're asked to find this angle here. So really, it's the same as this angle here, okay? So that means the vertical is our opposite side and the horizontal is our adjacent side. Okay, there's our horizontal, there's our vertical. So there are our numbers, and this is how we put them in. Don't mess up and put them backwards. And then we should get an angle approximately, I don't know, like something 65 point something. Okay. This one is 145. Okay. Now this type of question shouldn't take too long, but there's a lot of work, as you can see. Okay, there's no shortcut. This is the only way to do this type of question. Write them all out. Yeah? Everybody good? Okay. This is how long it takes to do these questions. All right. Should we take a little break now, and then we'll come back, and I'll probably do a couple more relativity questions. Relativity? Yeah, we'll just come back, take a little break, and finish up with this relativistic question. This one. Yep, we're almost done. Okay, so see you guys in like 5 minutes. Sound good? Okay, great. Okay, so is everybody back? Give me a thumbs up if you are back. All right. Good stuff. Okay, this last question, I believe it is the last one. Question 14 here. So we're talking about, we're not gonna do this part here, because that's about standard model antiparticle stuff. But what we are gonna do is part B. Okay, so B, C, um, D, and E. Okay, because it's going to talk about relativistic effects. Okay, so we read through this. What we got is asking us, what is the non-relativistic physics? Calculate the mean distance that muons moving at this velocity can travel. Okay, so non-relativistic, mean distance, so S times V times T. Okay. Well, I have velocity. Where's my time? Well, we read up here, muons are created in the upper atmosphere, blah, blah, blah. High energy in their own time frame. Muons have a mean life of this many seconds. We want the mean distance. Okay. So mean distance means mean lifetime. All right. Let's do this then. So that's it. V is this one. And then the time is the mean one, not the maximum. Please be careful when you read that, okay? And then we have that one, so 2.2. I'm not going to do it all, just that. That's enough. So you should be able to figure that out. Okay? Now it says, calculate the mean lifetime muons traveling at this as observed from Earth. So now we have relativistic effects because it's talking about observed from Earth, another frame of reference, as you can see, okay? So let's take a look. This is our time according to, in their own frame, muons have this much life. Now it's asking you what's the mean lifetime while traveling at that velocity. Okay, well, if we use our equation, okay, it should be TO over 1 minus V squared over C squared, yes? Okay, I'm just gonna check, and this is, I believe, from, what year is this? This is the SCASA one, 2020, okay? This question. So if I'm looking for this, I believe the answer for this is that one. And for this one should be 2.84 times 10 to the power of -5 seconds. So time dilation. We see that this is a bigger number than here, the mean of them. That makes sense. It should have a time dilation. So what is the actual mean distance traveled by such muons through the atmosphere as observed by Earth? So now we're going to be asked, okay, if this is how long they see it travel for, well, how fast do they go? Okay, well, according to this, there's the velocity they'll travel at. And so for this, we just want the actual mean distance. So another v times t again. And so we're going to use our velocity from here multiplied by our diluted time because it's observed from Earth. So dilated time, 9.2. So how do I know to use this? Because that's the velocity we're given. Could you say, oh, I want to use this one? I believe that is this. I'm not sure, but I believe that is that. You can work it out. Okay, and then this one, 2.84. And that is in kilometers. Please remember to convert. This is going to be in meters because we have meters per second, we have seconds. So you be careful when you write your answer that you convert it. Okay, so we have the answer for this come out to 8,000 something, 8,400 something. So we need to convert it to kilometers per kilometer, and that's what it comes out to, 8.49 kilometers, yes? Okay. Now, using information from the question, explain why a small number of muons reach the Earth. Wow. So I think from the beginning it says they don't last in their own frame. Muons have a mean blah blah blah. The speed blah 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 blah. Okay, it didn't really say anything, did it? Explain why small numbers reach. Okay. Well, according to Earth, or the mean time, if we look at how far they can travel according to our observation on Earth and compare that to how far they travel in their own frame of reference, there's a huge difference. Yeah? And because they last longer, their lifetime is much longer, then they will have, not that their lifetime is much longer, well, as observed by Earth, their lifetime would be longer. So that means they will travel much further. And so that's why some of them are able to travel to reach the surface of Earth. Okay? So that's it. Yeah. The lifetime so the mean lifetime sorry, there should be a gap there. The mean lifetime is longer as observed from Earth. So that means muons travel, live longer, and travel to the Earth's surface. So they live longer due to the time dilation effects. Okay, so can travel and reach the Earth, travel longer, travel further, and reach the Earth, and reach Earth. Whoopsies, reach Earth. Yeah, I know the mouse. I could write better, but I wouldn't be as fast. use the with use of calculation, explain why muons reach the Earth from the perspective of the muons. Okay, so from the perspective of the muons, why could they reach the Earth? Okay. Well, the distance that they would travel is um, is that far, I believe, right? What's the action as observed from Earth? Oh, okay. So here it is, according to um, the distance that they will travel. So what do we know? What about the length contraction, right? So according to them, if they're moving near the speed of light, then the distance from them, where they are, where they start, to the Earth, that distance will experience a length contraction. Yeah. So it'll have a length contraction experience a shorter distance. Okay. What is that length that we're going to use? What is the velocities that we have? So the length that they experience is what? The actual total distance traveled and the mean difference. Which one should we use? Anybody? What's your best guess? Wow. Just a plethora of volunteer questions, answers, I mean. No? Which one should we use, guys? What is the distance that it will experience? So Explain why the use of Earth from the perspective of the muons. So remember the muons. This is the length that they experience in the frame of reference. The length of the moving part. So if the space is the distance between where they start and Earth, and that's becomes the moving frame of reference. Okay, so the muon itself, the particle, has the Earth moving towards it. So this length now becomes, shorter, a length contraction. So what we have in terms of our distance, okay, becomes shorter now. So 8, I don't know what was the original 149 something? 8.4 something. Okay, there it is. 8.8494. Okay, and what is our velocity? Our velocity has to be squared, guys. And then I believe the velocity is given to us, right? The astral meter through the. Okay. So there's the velocity given to us. Mean lifetime, range, yeah. So we gotta use this one. There it is. There's the velocity given to us. 2.991 squared over 3 squared. Times 10 to the power 8 squared times 10 to the power 8 squared. I don't think we had to include that part because just don't. So what do we get from that? Just gonna check on my calculator. Does it say the distance? Oh, approximately 10 kilometers. Whoops. Sorry, not this one. So we do know the distance is approximately 10,000 kilometers. So 10,000 meters, I mean. Okay. Okay. So I'll put that on my calculator, come up with this. We get the distance that it seems to travel. And then we're asked to explain, okay, so that's the distance it seems to travel based on the length contraction of that distance. So once we know that, we can find out the time it takes for it to travel that far according from its perspective, yes? So there's that length contraction. It's traveling at that velocity. And what happens is we get a number. We get a number that we now compare to its mean lifetime. If that number is larger than this, that means the muon has enough time to reach the Earth before it's the end of its life. It reaches its half-life. Okay? So we got to beat this number, 2.2 times 10 to the 14. Okay, so this should be greater than that, 2.2 times 10 to the negative 6 seconds. Okay? We'll check to see if that's true. If it is, then we know it will reach the Earth's surface. And what we get from this calculation is 259 times 10 to the power of negative 6. And we can see that it's true. It's slightly longer, but you know, such a short time, that's enough. Okay? Does everybody get where I got all this and why we did this? Again, why did I choose to do a length contraction equation here? From what understanding do we know? Well, it says from the perspective of the muon. So that means the space between where the muon's created and where it will land or touch the Earth, that space is the distance and the direction of its velocity. So that distance, it will experience a length contraction. Now that distance, I originally said it was this, but it's not. It's actually this one because that's where it starts. It's created there. And so the 10,000 is the proper length according to the stationary or the moving frame of reference, which in this case is an observer on Earth. And that space between the muon and Earth is the moving frame of reference. Okay? So this is LO, or the proper length is in the moving frame of reference, and that is the space between Earth and where the muon's created. So we take that, we apply the length contraction, we get this distance. And then that distance in the frame of the muon, in the the reference frame of the muon, is how far it has to travel going its velocity. And when we do that, we get the time and we compare the time, and then we can definitively say, oh yes, this is why it reaches the Earth. It has enough time before its half-life is finished. Okay? Is there? I think that's it. Yeah. Everybody good? Yeah. This question was a bit long. Thanks for sticking around. If you guys have any other question for any of the other problems, let me know, and you stick around and you can ask me that question. But otherwise, we're good.